get started. Okay, welcome back. I hope everyone enjoyed their break and everyone survived the storm safely. If you had any issues, please talk to me and we'll talk about, I guess, more time or whatever's needed. But good luck. I probably won't give you any because it wasn't that bad, was it? Anyone? No, okay.
It was horrible. We need at least 2 weeks to recover.
Okay, that's what I thought. Good. Well, speaking of, never mind. Well, today we'll talk about Deadlock, something completely different than the storm. So, what is Deadlock? Have we talked about this before? Ooh.
When something gets locked out and never unlocks.
Or like when two resources are trying to get for the same thing and neither one can get it.
Right, so they're deadlocked. They're basically sitting there doing nothing. Right, so we're going to talk more about deadlocks and how to avoid them. What I find funny about this chapter is it talks about deadlock and then halfway through it starts talking about all the different ways we can avoid it, and then it finally mentions, oh hey wait, by the way, no modern operating system does this. So we're going to be learning some theory about stuff that might be useful one day but currently is not at all. Everyone okay with that? I mean, everyone understood what I just said? You don't have to be okay with that.
We an option.
But if you're not okay with that, I understand, but too bad. Great, yeah, talked out deadlock problem, how to prevent it, avoidance, detection, and recovery. Great. Thanks. All right, so the deadlock problem, block process, each holding a resource and waiting. So here's the example down here. How could this be deadlocked?
Because P0 waits, grabs A, then interrupts, and P1 grabs B. Now P1's waiting on P0 to finish, and P0 is waiting on P1 to finish.
Okay, good. Any comments, questions? No? Great. Perfect. They like to do a bridge. I kind of think this is funny. But traffic in only one direction. Just think of this as 2 lanes on each side, but then there's a bridge which has to be 1 lane. Each section of the bridge can be viewed as a resource, of course. Deadlock occurs and can be resolved if one car backs up, and that would be an example of preemption. Do y'all see what's going on? The cars on the bottom going to the right, on the top they're going left, and then they have to somehow get to the bridge, and the idea is 2 cars are now meeting in the middle. Of course, this portion in the middle could be a mile long or something, but we'll just say it's that 2 car lengths wide just to make it easy. So, all right, they tell you if deadlock occurs, it can be resolved if 1 car backs up. And this is an example of preemption. Why is this preemption?
Because you have to know that you're in a deadlock situation. Or that you could be in one.
Okay.
You have to preemptively think about when this could occur and fix it.
So these 2 guys are waiting, and they are preempted saying, oh, whoa, you on the left, you need to back up. AKA you on the left, you need to release your lock and let the other guy go through. So it's preempting that process. It's before it can complete, it basically backs up or takes it out. Several cars may have to be backed up if a deadlock occurs. Why is starvation possible?
Because if you don't have one backup, they just sit there and idle.
Okay, that's an example, one example of starvation. That's starvation from deadlock. But how could you not have deadlock and still have starvation?
The right side allows cars through indefinitely.
But the other side?
Just sits there and waits for all the cars that have been backed up forever.
Great. Is that very nice?
No, but that's reality.
That's
Get over it.
I noticed the drivers here are actually nice about that. Here, you can have your turn, although sometimes it gets annoying. No comments on that one. I thought I'd get something.
No, I'm just happy so when the driver uses their turn signals.
Oh, okay.
Here.
No, those are just decorations.
Oh, okay.
Keep them. All right, system model, what do we have? Different resources. Yeah, with CPU, cycles, memory, I/O devices. Right, so you're going to have these resources, and each resource has certain instances running on it. And they can request it, they can use it, and then they can release the resource. All right, great. Okay, these are the 4 characterizations of deadlock, and these are the 4 characterizations you should know. And these 4 will probably come up on a midterm. So here they are. They're in bold, and they each have their own block next to them with the definition, and we will go over these again in the next slides. So hopefully you understand that these are important. But basically, you need these 4 conditions to hold simultaneously for deadlock to occur. So all 4 have to hold. First off, mutual exclusion. Namely, only one process at a time can use a resource, aka there has to be a critical section where only one process can enter, and of course one process can exit. So that's mutual exclusion. Hold and wait, so a process holding on at least one resource is waiting to acquire another resource held by other processes. So what that's saying is, if there's only one thing that needs to be locked, then, or one critical section or one piece of resource that needs to be held, you're not going to have deadlock because only one person can grab it, do it, and then he's going to release it. But so you're going to have at least 2 in order for some type of deadlock to occur. Good so far?
At least 2 processes or 2 resources?
2 resources. Obviously 2 processes as well. That would be... yeah, okay, I shouldn't say that. You could have one really poorly written process. But anyways. No preemption. All right. Namely, the resource has to be can only be released voluntarily by the process holding it. In other words, the kernel can't jump in and say, "Hey, you, let go," or a kernel jumps in, or in this example, the kernel would probably be, a police officer saying, "Hey, you, back up," or something along those lines.
You can't have an external.
Yeah, there's no external saying you're being bad, you need to get out. So there's no way to preempt it. And then lastly, so you have those 3 conditions that basically hold the foundation of what needs to be available to create the deadlock. And the last one's a circular wait, where there's some set of waiting processes, has to be 2 in general. And one is waiting on something by the other, which is waiting by something on the other, and then eventually it loops back around to where the guy at the end is waiting on the first one. So the reason why they call it a set is because it could be 2 or it could be 4, but somewhere there's a cycle where everyone's waiting eventually. Really what this is saying is process 0 is waiting on something where eventually if you follow the line, it comes back to waiting on itself, is the way I like to think of it. With those 4 characterizations, you have deadlock. Any questions on those? Good. Just to make sure it's clear, if we did not have mutual exclusion, why would we not have deadlock?
Because they could all just enter.
Because they all could just enter. There's no critical section. If we didn't have hold and wait, how come there's no deadlock?
Because then it wouldn't be waiting on something else.
Right. It's just there's nothing to wait on.
It would just do its thing and go.
And no preemption. If we had preemption, why would that avoid deadlock?
Because something would give up its resource until the other one relinquished it.
Okay, so you're on the right track. So the idea is that if he was holding onto a lock, someone else, the kernel, would say, you're now going to give up your lock. aka we're going to preempt you from continuing and roll you back. And then lastly, circular wait.
Because eventually, if you didn't have that, one of them would finish its
complete,
task.
yeah.
There's always someone that could fit. Yeah, if you didn't have circular
Go back
wait,
up the chain.
then that means that there is some process that can be working, and therefore there is no deadlock, right? Okay, great. So we're going to go into graph theory. Did anyone not see this? Anyone not see this coming? Graph theory. Did y'all think no graph theory would be in this class?
Possible.
Possibly. Okay. So we have graphs, and then we're going to actually show what this looks like with the graph. And hopefully this actually gives you an idea of why a lot of these algorithms are not in place inside of operating systems, because most graph algorithms, how efficient are most of them?
Not good.
Not good. And if your operating system is supposed to be highly efficient, are you wanting to be running, an extra shortest path algorithm or something like that all the time? The answer is no. I'm being rhetorical. So, since they're shown this way and the analysis is done using graphs, and we pretty much have to use graphs, that's why a lot of these algorithms are not used. But anyways, set of V vertices and set of edges. Wow, okay, that's great. So the V is actually partitioned into two types. So your vertices have two different types. It's not like a standard graph where every node is the same. Now your graph has different types of nodes. So it might be a little different than what you're used to, but you'll have your set of processes and your set of resources. And then a request edge, notice that the request edge is going from a process to a resource. That means the process is requesting the resource. And the assignment edge, aka you have been assigned this resource, is going from the resource to the process.
Why is process 1 always doing the requesting?
Oh, that's a terrible typo. That should be process I. Man, that would solve our problems a lot, wouldn't it?
Yeah, because the request is directed edge P1 going to R.
That's P sub I.
Yeah, and RJ going to P sub I.
That's P sub 1.
That should be an I. That is not a 1.
This is not the process you're looking for.
Not the process you're looking for. So if you have a process, hey, look, circle resource we'll make with squares with 4 instances or 4 resources that I could grab. So these are 4 copies of the resource. Process 1 could, process I, whew, got me saying it, can request the resource by arrow going over, and then P process, is that still an I?
Mm-hmm.
I is holding an instance of RJ. Notice that the arrow is going from one of the instances inside of the resource to the process.
So is that R sub J sub
0, sure. Or A,
K?
K, sure. R sub J sub K. It's just more layers. All right. What was this saying?
Process 1 requested a resource, but it was given to process 2. Who requested something from resource 3.
Oh,
They
so
gave it
hold
to
on.
process 3.
This is, you're on the right track, but everything needs to be present tense. P1 is requesting R1, but our process 2 is holding R1. It's not that they have requested or have given, it's what currently is being held. Yeah, and then process 2 is requesting R3.
Process 3 needs to finish its tasks.
Well, process
Process
3 is holding
Right.
resource 3, right.
So process 2 can finish its tasks, so that process 1 can finish its tasks.
All right, sure. What about this down here?
Not effective. But process 2 is holding resource, an instance of resource 2,
Yeah.
but so is process 1.
Correct. And there are 2 instances of resource 2. Is there deadlock?
No. We do not have circular weight.
How could we make this into deadlock?
If process 3 needed resource
2.
Yes, resource 2, you got it. Now we have deadlock.
Resource 4 is going like nobody wants me.
That's why all of you.
You have everything you wanted, but no.
You wrote your code smarter.
All right, so now we have deadlock. Why do we have deadlock?
Because all 4 of the things.
There we
We have
go.
mutual exclusion. We have a.
Hold and wait.
I was kidding there. No, you got it now. Go ahead.
What's the third one?
The third one is.
No.
No preemption, and then circular weight.
All right, and where's the circle?
Circular whatever.
Where's a circle?
P1 to
R is
R1.
waiting on either P1 or P2.
Yeah, there's multiple
Which are
circles here.
waiting on P3.
Yeah, so one circle goes P2, boom, 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 boom. The other circle goes P1, P2, over to P3, down over, back to P1. All right, but here's an example of how you can have a cycle with no deadlock. Did that just make this problem more difficult or less difficult? Or actually, first off, why does this not have deadlock?
Because when P2 completes, P1 can complete.
Well, P2 and P4,
Yeah, P2 and P4 can both complete.
and release their resources, which,
Would give P1,
right.
well, P1 or P3, depending on which one completed
Well, I mean, once P2 completes, P1 can grab its resources and do its thing.
Or P4 can complete, then P3
But
can
that
complete, then
P4's
P1
process
can
doesn't
complete.
make any difference since you have 2 instances it's drawing from.
Sorry, say it again?
Well, P4 is only drawing from R2, one instance.
Right, it's
And-
holding. Yeah, holding.
Right, so it does need to, it won't make a difference to that because, oh wait a minute, it does, never mind. Because P4 is holding one, RP3 can't have it. Okay, gotcha.
So if we were going to come up with an algorithm to detect deadlock, the fact that a cycle can exist but no deadlock, does that make it easier or harder?
Harder.
Harder, right. Yep. All right, basic facts. All right, if a graph contains no cycle, no deadlock. All right, well, that's great. That's an easy check. Actually, that's a pretty easy check. That's an O of N check, which actually is still slow for the kernel, but, you know, not bad.
But when you say no cycle, you're meaning like no process requesting a resource. Is that
No
what-
cycle. So here we have a cycle because we can go P1, R1, P3, R2 back to P1, so there's a cycle. Where if I were to break this edge, there would be no cycle because there's no loop or no ring,
Circle, okay.
no circle. So a cycle is simply a circle. If a graph contains a cycle of only one instance per resource type, then deadlock. Okay, that makes sense. Does it? Yeah, so if you were back here and there was only one resource with the cycle, you would have deadlock, because in order for this to be a cycle, this connection would not have to be there and this connection would not have to be there, therefore there is a cycle, and now you have deadlock. Okay. If several instances per deadlock, per type, possibility of deadlock. Oh. All right. So methods for handling deadlock. The first one is my favorite. Ensure the system will never enter a deadlock state. How can we do that?
Good coding.
Good coding. Don't turn it on.
Because you have processes, and you're
We could ignore race conditions.
ensure that whoever developed the operating system is also doing the programming. And you said good programming, because there's no way you're
Even then, I'm pretty sure the person would mess up at some point. Unless, Matt, you think you could write a perfectly deadlock-free
I like
multiprocessing?
that last one the most.
Ignore the problem
That's
and
kind of
pretend
my
never.
style too.
Right. Allow system to enter deadlock state and recover. Ignore the problem. Pretend that deadlocks never occur in the system. This is literally what we do. I'm not joking. That is literally what we do.
So in other words, good coding. The only way.
Sounds like a programmer's problem to me. Not my problem. That's fortunately the way we go about it. And I've said it multiple times, but why is that?
Because people are lazy.
People are lazy. Okay, I didn't say it multiple times. So why do you think the operating system doesn't solve this problem for you?
efficiency.
Efficiency, yeah.
Why solve the problem? We'll just kill both processes, they can start over.
Oh, no, it just runs forever.
Oh,
No,
the
actually, it
process
just
runs-
now it doesn't run because
should
now we
time out.
block. No, it doesn't time out. It's just waiting.
Oh, the operating system won't do something about that?
No. Well, how do you know it's not waiting? How do you know it doesn't need waiting a year for something to come back as opposed to a second? The operating system doesn't know how long a process is supposed to wait. Well, the operating system's not going to do that.
Oh, okay, gotcha.
That's someone else's problem. All right, so deadlock prevention, which is going to be the best way to go about it. Let's see, mutual exclusion, not required for shareable resources, but must hold it for non-shareable. Okay, so all it's saying here is you can try and minimize mutual exclusion, try and minimize how much of the critical section there is. That should be intuitive, hopefully. Let's see, hold and wait.
How does it apply to shared memory? Basically kind of the same thing, you want to reduce the amount you rely on.
So in shared memory, we're not using locks necessarily.
But if the processes have to if you have to, you can't have the data messed with before, I mean, it has to be exclusive because let's say they're both modifying the shared memory.
Right, okay. All right, hold on a
We
second.
go back to what we did before.
Yeah, no. They're all connected. So let me see if I can be. So shared memory is a mechanism to basically share data between processes. Now, by itself, it's not going to provide any locking, which means that race conditions can occur depending on how that shared memory is used, right? So if you want to avoid erase conditions, in general, you have some type of locking via a semaphore or mutex or something monitors or something else along those lines. Now, when you use those, which are separate than shared memory, you're using those to come up with a critical section or critical path or portion of the code that only one process can be in. And that's the mutual exclusion principle that we're talking about. Great question. Hold and wait. Must guarantee that whatever a process requests a resource, it does not hold onto any other resources, or at least minimize it. So what you can do is basically make sure there's only one lock whenever you request a resource, which may be hard to do in certain situations, because if you need multiple resources, you'll probably want to have one master lock for it, but then that can have performance issues when you are trying to, when you have one lock but you're requesting things that other people may only need one of. Do you understand what I'm trying to say? Yeah. Okay. No preemption. Well, basically add preemption. Come up with some way to stop a resource from getting the lock. Why is this hard to do?
What if they're in the middle of writing to it?
Right. Writing to it. Well, the idea is that you would have, you're trying to grab multiple locks. And you're in the middle. Yeah, what if you're in the middle of writing it? That's probably the best way to think of it. Because there's no way to guarantee that they're just grabbing a set of locks. So the problem with preemption is you're going to have to roll back somehow everything they did, which is pragmatically speaking not possible.
You have constantly keeping reset points or whatever.
You got it, yeah.
And completely inefficient.
And completely inefficient, right? So unfortunately, preemption is can be very difficult. And then circular wait, which ends up being pretty much mutual exclusion you want to work on minimizing, but there's only so much you can do. Hold and wait, same thing. Preemption, you kind of just give up on. I mean, these are great ideas if there was a good practical solution to them. Circular wait impose a total ordering of all types and require that each process request a type and increase the ordering of enumeration. Just to make sure that is crystal clear. Oh, look, I get down my board. So we have process 1, process 2. How does that look? Oh, right on that glare. Nice.
Oh. Hold on. No, that doesn't make a difference, does it?
Rare, yeah.
It does, it just changes where the glare is.
Yeah, that's fine. So this one can wait on resource 1, wait on resource 2, and then signal resource 1. I'm just making sure this is perfectly clear what we're talking about. Resource 2. And then over here, the issue is if he tries to wait on resource 2, and then afterwards tries to wait on resource 1, and then signal resource 2, signal resource 1. So all circular wait is saying that make this once. Pick one. It actually doesn't matter which one you pick. Pick one and stick to it. So make sure you copy this ordering to every process so that they're always grabbed in the same order and then released in the same order as well.
I thought the release didn't matter. I thought the release didn't matter.
So in general, the release does not matter. Let's see. Can we come up with a way the release matters? No. The release really doesn't matter. unless you start doing the signaling in the reverse. Yeah, there is, doesn't matter.
You just pick one order and it's-
Pick an ordering and make sure every process is doing it. Either this one or the other. It doesn't matter which actually you choose, as long as they're all consistent. Because you want to avoid this cross problem. So in other words, if someone needs a certain set of resources, there is a specific ordering of how you request those resources.
So the first process requests the first resource, the second process requests the second resource.
Sure, just there has to be an ordering to it. That's all it's saying. All right. All right, so wait a minute. Let's go ahead and stop.